Now we take a look at the examples of measures constructed out of the Rees representation theorem. So our first example should of course be whether it should answer whether the Lebesgue measure can be constructed out of the Rees representation theorem, and of course the answer is yes, as I mentioned before, that the Lebesgue measure can be constructed using the Riemann integral functional. Secondly, we have seen the Dirac measure. This can also be constructed using the Rees representation theorem. And lastly, I will just give an example of what are called Har measures. So these are measures on locally compact Hausdorff topological groups. So these are groups which have an underlying space with a topology. So the underlying space of the group is a topological space, and it is locally compact Hausdorff. A topological group, in a topological group, the group operations are continuous with respect to the topology. So group multiplication and inverse operations are continuous with respect to the group topology, and we will construct not for general groups but only for G equals R star, which is the group of the multiplicative group of non-zero reals. So with the multiplication operation. So let us look at how to construct the Lebesgue measure from the Rees representation theorem. So first is the Lebesgue measure. So we have x is RD, and we take the linear functional, the positive linear functional which I will denote by lambda r, which is from CCRD to C, and this lambda r is given by the Riemann integral. This is the Riemann integral of f. So notice that since f has compact support and it is continuous, f is Riemann integrable, and you can in fact replace Rd here by some large box that contains the support of fx dx. So of course this lambda r is a positive linear functional as claimed. So one can check that lambda r is a positive linear functional on CCX. So by the Rees representation theorem, it induces a Radon measure mu r on Rd, and so the claim is that mu r is nothing but our Lebesgue measure on Rd. So to show this, it is enough to show that mu r and m agree on open sets, because remember that the outer measure that was defined in the Rees representation theorem was defined using measures of open sets approximated from above, And so if we have this equality on open sets, it's enough to show that mu r equals m, because then the outer measures will be the same, and then the sigma algebra generated by the Carathéodory measurable sets will be the same, and so the measures will also be the same. So we need a few results that I will leave as an exercise. So the first is that any Riemann integrable function f on Rd is Lebesgue integrable, and in this case we have that the Riemann integral of fx dx of f is equal to the Lebesgue integral of f with respect to the Lebesgue measure. So on the left hand side we have the Riemann integral, and on the right hand side we have the Lebesgue integral. So the Lebesgue integral can be seen as a generalization of the Riemann integral, and if f is Riemann integrable, then it is Lebesgue integrable, and the two concepts agree for Riemann integrable functions. So that's the first one. Second point is that m star of E, the Lebesgue outer measure, can be written as the infimum of sums of m star uj, j equal to 1 to infinity, such that E is a subset of the union of uj's, and each of the uj's are open. So for example, you can use that U open is a countable union of boxes, of almost disjoint closed boxes, union of almost disjoint closed boxes. So once we have this, we have already seen that the outer measure defined in the Riesz representation theorem was defined using the mu's that were defined on open sets using the functional, and then we define the outer measure like this. So if the measure from the Riesz representation theorem agrees with the Lebesgue measure for open sets, then the outer measures will also agree, and then the sigma algebra generated by the Carathéodory measurable sets will also agree, and the measures will also agree. So it suffices to show that mu r u equals mu for u open in Rd. So first suppose that mu r u is finite. So let epsilon be greater than 0 and choose f less than u such that mu r u is less than or equal to lambda r f plus epsilon. So this is because the mu r is the supremum of all such lambda r f's. So you can choose one such which is close to mu r u, and this is nothing but the integral by definition of lambda r. This is the Riemann integral of f, and now we know that this is also the Lebesgue integral of f, and this is nothing but well, this is less than or equal to the integral of chi u dm plus epsilon, since f is less than or equal to chi u, and the last is nothing but mu plus epsilon. So this means that mu r u is less than or equal to mu. Now for the reverse inclusion, let un be the intersection of u with the open ball of radius n and center 0, so that the measure of un is finite and u is the union of these uns, n equal to 1 to infinity. And now for each n, since the measure is finite by the density of CCRD in L1, we can choose a function fn in CCRD with values in 0, 1, such that 0 is less than or equal to fn is less than or equal to chi un, and the L1 norm of chi un minus fn is less than or equal to epsilon. But what does this mean? This means that the integral chi un minus fn dm is less than or equal to epsilon, and now both are finite, so this is mu, and you get minus integral rd fn dm, which is less than or equal to epsilon. So you can take it on the other side and you will have less than or mu is less than or equal to this integral plus epsilon. And now we have seen that Lebesgue integral and Riemann integral coincide for continuous compactly supported functions. So this is equal to rd integral over rd fnx dx, where this is now the Riemann integral of fn plus epsilon, and on the left hand side you have lambda r fn, so sorry, this is un, lambda r fn plus epsilon. And now note that since fn is less than or equal to chi of un and chi of un is less than or equal to chi of u, this means that fn is less than u. So fn has compact support inside u, and so this is less than or equal to mu r of u plus epsilon. And now we can take the limit on the left hand side to get mu less than or equal to mu r u plus epsilon by upward monotone convergence theorem for the Lebesgue measure. So this implies that mu is less than or equal to mu r u, and we are done. So we have shown that for open sets, so we assume that this was finite, and I leave it to you as an exercise to show this for the case when this is infinite, but then again you can use a limiting argument as I have done here. So I leave it as an exercise. So this shows that the Lebesgue measure can be constructed out of the Riemann integral for functional, and in this way we can see the Lebesgue integration as a completion of Riemann integration. Another example is the construction of the Dirac measure on x. We have already seen what it is. So if we fix a point x naught in x, then mu x naught of a set E is equal to 1 if x naught belongs to E and 0 otherwise. So I will construct this measure out of the Rees representation theorem by considering the evaluation functional which is given by, so I'll write EV x naught from x to 0 1, and this is by definition, this is over CCx to 0 1, and if you apply a function with continuous function with compact support, then by definition this is f of x naught. So this is why it's called evaluation, because it's evaluating the function f at the point x naught. And as an exercise, I leave it to you to check that the induced measure from the evaluation functional. So first one has to check that this is a positive linear functional. This is quite straightforward, because if f is positive, then fx naught is positive, and linearity is obvious because f plus g is defined using the pointwise addition, so it is also positive, it's also linear. And now we have to check that the induced measure from EV x naught is indeed this Dirac measure mu x naught. So I leave it as an exercise, and as a remark, note that if xi I equal to 1 to capital N is a collection of points of x, and alpha 1, alpha 2, alpha n are positive real numbers, then the finite linear combination of alpha I EV xi, so let me denote EV xi alpha I, this is the finite linear combination of the evaluation functionals with coefficients alpha I. This is also a positive linear functional. So the induced measure over these points I equal to 1 to n is given by the following formula, is equal to sum of alpha I if so it's a sum of alpha I k equal to 1 to say m if xi1 xi2 up to xim belong to E and 0 otherwise. So the maximal set of points that belong to E will contribute to this measure, but it will be 0 otherwise. So it's a generalization of the Dirac measure, and you can construct this using the Rees representation theorem. Now the third example is the Har measure on a topological group. Well, we also want it to be LCH, locally compact Hausdorff. So a Har measure, so let G be a locally compact Hausdorff group, topological group. Then a Har measure on G is a Radon measure on G such that, so Radon measure, let me denote it by mu, such that the measure of GE is equal to measure of E, where GE, so this is for any Borel set E inside G, and GE is by definition the set of points G times E such that E belongs to E. So here we are just using the group operation. So this is called the left translation invariance property, invariance, and in fact this is what's called a left Har measure. So you could also have the right Har measure where G acts on the right, and you could also ask for both, but it is rare. So as an example, we have RDM, where RD is taken as a topological group with the addition with the Lebesgue measure M. This is a Har measure, because M is translation invariant. So this group is an abelian group, so left and right actions are both the same. So this gives you a Har measure. So that's one example. Another example is if G is the multiplicative group of reals. So this is R minus 0 with the multiplication operation, and if you define for f in CCG lambda f as the integral of f over R star f x dx over mod x. So this is over the set R minus 0, and this is the usual, you can take it as a Lebesgue integral, and if you define this functional in this way, then it is again a positive linear functional, is a positive linear functional which gives the measure via the Rees representation theorem given by, so let me denote M M cross as the measure induced by lambda. So M cross lambda of A, where A is a Borel subset of R, is given by the integral over A of dx over mod x. So for example, M cross lambda of an interval AB, so A minus 0, so of course A is a subset of R star here, so A will not contain 0 anyway. So AB minus 0, if this interval contains 0, then we remove it from this interval, and so this will be the integral. Well, let me take it both positive so that it's easier. So then there is no 0 inside, and so this is simply the integral from A to B of dx over mod x, which is the same as integral A to B dx over x, and this is ln B by A, and it is left invariant because m star lambda of C times this interval AB, for example, this is nothing but the measure of the interval CA CB, and this is nothing but ln of CB by CA. Here again I am taking C to be positive, strictly positive. So then you will have, you can also take it to be strictly negative, but then you will have ln CB over CA. So this is again ln B over A, which is m star lambda AB. So this is with respect to the multiplication group operation, this is invariant. So this is a Har measure on the group of multiplicative non-negative reals.